Thank you. Thanks for coming. It's a pleasure to be invited here to the conference from NuScale Power. A little bit about myself. I spent 26 years in commercial nuclear power. I was mostly operations, control room operator, control room supervisor. Did 8 or 9 years in work control, scheduling and planning outage and online work activities. And I've spent about 10 years out in training control room operators in the nuclear field. 2017, I left that wonderful place and went out to Portland or out to Corvallis, Oregon to work for NuScale Power. And if you look online, their headquarters they say Portland, Oregon, but the main office is in Corvallis. So all the engineering and all the technical development is mostly done out of Corvallis, Oregon. So we had our design safety certification approved about 3 years ago by the NRC. So from a reactor safety standpoint, the federal government has approved our design. We're submitting a site standardized design application in coordination with the owner, UAMPS in Idaho, and the plant's going to be at Idaho National Labs in the property contained by Idaho National Labs. About 3 weeks ago, we IPO'd and went public, which was a big, exciting time. I got to see our founder and COO ring the bell at the New York Stock Exchange, and they had a lottery, had about 18 folks that got to go along and watch them ring the bell in there. So that was pretty exciting. So a lot of big changes are happening at NuScale. A lot of other interested parties wanted to understand or explore the options for a small modular reactor for their country or their community. And I made just the right time here. All right, so this is our overview. It's released for public disclosure. It's through our external relations, so it can be shared. As our disclaimer, a lot of our work was developed under DOE grants, so we have to give DOE credit for some of the work that we did for its development. So you'll hear the term SMR, nuclear. How many people by hands are familiar with nuclear power? It's like, okay, I got a few people. Okay, that's good. So if you hear SMR and you know that nuclear power industry is loaded with acronyms, they love their acronyms. So SMR will be a small modular reactor. It's scalable, safe, reliable, carbon-free. It's an artist's rendition of what a site would look like as built. Formed in 2007, initial concept was developed at University of Oregon and then later licensed out to LLC, which is NuScale Power. And Fluor was a major investor, wanted to be involved in the construction and building of most of the non-nuclear components. And we'll get into a little bit of how the uniqueness of it. Sargent and Lundy has been building a lot of the nuclear aspects of it. They're more familiar with the nuclear aspects of it. About 628 patents involved in this creation of this design. There's about 430 people working in 5 different offices. There's quite a large investment already in the NuScale design. The bottom picture you see there is our simulator in Corvallis, Oregon. And that would be for our 12 module plan. That's what we started off with, a 12 module design. When we went later on, when we got to talking dollars and cents with buyers, the Idaho project, it didn't seem feasible to have a 12 unit module. So we have a 6 unit module that we're designing for them. It's roughly half of the 12, but the function of the plan is exactly the same no matter how many modules or how many units you have. We have a mission statement. We want to be smarter, cleaner, safer, cost competitive. I like to add in also easier. It's quite a bit easier to operate than a conventional nuclear power, and that's we'll talk a little bit about that in our training sessions because we want to keep the training as simple as possible. So if we were offered the opportunity to replace a coal plant site or some other generation site, we could just, it would be easy transfer of jobs from the coal site to the nuclear plant for maintenance, operations, and other things. So we wouldn't have to spend a lot of time or money retraining or having extensive training for personnel. Again, at 12 NPM, NPM is the module, the nuclear power module. Gross output of 924 megawatts. It's trademarked as a Voyager plant. And so approved in August of 2020. We have a 4 and a 6 module design. And essentially it's the electrical output of the generator. It's a basic steam cycle. So each module generates steam. The steam goes to a steam turbine, and that turbine connects to a grid, and the more you add together, the more you get out of it. About 77 megawatts electric is what each module will put up. So you could just add them up. In addition to that, you could order a 12 module plant and only install 2 modules because that's all the power that you needed right now. So you'd only have, and then as your demand expanded, you could add modules and units as time went on. We're involved in some microreactor concepts, nothing that's officially ready to share yet, but there's a lot of activity going on with that and a lot of research and development going on. There on the left is a picture of what the NuScale power module would look like. So this module is assembled and constructed in a factory that is somewhere offsite, a centralized factory. And then that module is shipped without any of its fuel, and nuclear fuel comes separate, but the module is shipped by a barge or truck or rail to the site. And we believe that there's a lot of efficiencies to be gained by having a modular factory built assembly. And that module, in the reactor pressure vessel and the containment is all part of that same module. Number 5 there, you'll see that is a side view of what the reactor building would look like. So the modules would be stood up vertically in those columns, and that's where all the miscellaneous steam piping, hydraulics, water, all the systems would tie in and hook up into that operating bay. When the fuel was expended for the uprated module, it's about 18 months of operating time. You would shut down the module, disconnect it, pick it up with a crane, move it over to where you, right underneath the yellow machines where you would disassemble it and refuel it. The other remaining units would stay online at 100%. So your total loss would be 77 megawatts for the outage duration, which we're now scoping for 10 days for the refueling outage. Again, another shot of the control room, very cyber secure, multi-module control room. We've got approval to operate 12 reactors with 3 people in the control room, which is very competitive to legacy plants. One unique thing, I'll go back to number 4, the reactor coolant system, the water that flows around the reactor. The propulsion of that is all natural circulation. So there is no electric pumps that pump the water around through the primary. It's just as the water heats up and its density goes down, it rises, and that creates the flow. And then it gets cooled off by the steam generator, and it falls back down and recirculates around. So that's at power and shut down. If anything goes wrong with the module while it's operating, we have valves that are in the reactor pressure vessel that will open up. They're ECCS valves that will open up, and it actually will drain some of the volume of the reactor coolant system into containment, and then containment becomes your heat sink to cool the reactor. And that whole module is sitting in a pool of water, so all that heat's rejected to a large pool of water. So that's how they can stay shut down without any power. They don't need any electricity to circulate to keep the reactors cooled down to safe. As another side view, this would be a 12 unit plant, so just a cutaway view. Our 6 module plant looks identical to that. They call it the ultimate heat sink. The water that sits in the reactor pool is about half the size for a 6 unit plant as it would be for a 12 unit plant. 12 unit plant's, I think it's roughly 12, 13 million gallons of water in that pool. You can see the reactor building is all below grade. It's an aircraft resistant enclosure, so it's both seismically secure and protected from above. Different module design or different plant designs. There's a 4, 6, and 12 unit design. They're all the same. The modules will all be identical. The final uprated for the reactor power output is 250 megawatts thermal energy. So it takes 250 megawatts of thermal energy to extract 77 megawatts of electricity. And that's just the efficiencies of a steam cycle with any steam plant, no matter what the heat source was. If it was coal or natural gas or oil, they're roughly the same. So one of the things that we like to talk about is our triple crown of safety, and this is very unique to the NuScale design. There's no operator action that is required to keep the reactor safe and shut down. There's nothing the operator could do to make things worse for any accidents that we analyze for or make things better. The module can simply de-energize, lose power. It transfers over to emergency core cooling system, and it sits and rejects its heat to the pool indefinitely. As the pool water evaporates, your decay heat load drops down to a point where just air circulation will keep the reactor cool forever. So there's no required actions to have electricity. There's no safety related power requirements for the design. Another interesting thing is the emergency planning zones are all going to be contained within 35 acres of the plant footprint that it takes up. So you don't have the 10 and the 50-mile exclusion zones and protection zones that you have for larger reactors to plan for their emergencies, and they have to have sirens, and you have to have evacuation routes planned out for people that may live in that area. And you have to design the plant to be a function of that area. With our design, the reactors are so much smaller. You don't have to have that zone out so far. So your footprint is your emergency planning zone. Built in a factory, containment and the reactor vessel are all together in one product. They're could be transferred by track, rail, or barge to the plant site, where they're put in the machine inside the reactor building that basically takes it from a horizontal state to a vertical state, puts it in the ultimate heat sink, and then we can disassemble it and load it with fuel and put it in its operating bay and run it. But you could have a 12-unit plant and only use two modules if that's all you needed power for. So when we started looking at for our customer for UAMPS, the 12-unit, even if they only wanted to buy 6 modules, they still didn't want a plant size that was that large. And we had some unique challenges for the UAMPS design, in that they wanted to have the steam out of the steam generator cooled by air-cooled condensers vice a circulating or evaporative water system, because the plant was in an arid area and the availability of water may be in question, and just using water for cooling and evaporating it didn't seem very environmentally conscious to us either. So we pursued that. That jumped up the cost a little bit to have a different cooling system, and so the 6-module design worked out a little bit better for them. Natural convection for cooling, seismically robust, simple and small. The reactor core is about 1/20th of the size. It uses, currently right now we're using what would be Framatome, or originally Westinghouse 17 by 17 fuel assemblies, just like all virtually all the pressurized water reactors in the United States use. It's virtually the same fuel. The only thing different about it is about half the height of a conventional fuel assembly, but the construction is the same. So we have unlimited coping period for the reactors, showing you some differences between different generations of current nuclear plants. Generation 2 reactor, they can only cope with issues for about 4 to 8 hours if they have lost power. So they have batteries and they have backup power, but they have to get their AC power back to prevent them from going into a lot of their emergencies or transients for shutdown. Generation 3 and 3 plus, about 72 hours with no operator action. Generation 4 is about 8 hours also. NuScale is unlimited, no operator actions to support the cooling. So it saved us a lot of design and money when we went to design the electrical system because it was a lot easier to design. We still are going to have backup diesel generators, but they are not safety related. They're not required. They're just for give people confidence. Our batteries that we have will monitor the plant for 72 hours after a loss of power. So that you won't, there's nothing that you can do to take an action, but you can monitor the status of the reactor for 72 hours. And then you could bring in a diesel power and recharge those batteries so that you could get indefinite time. Small emergency planning zone. You can see on the map, like a typical large scale, the zone that you have to show protection for. It makes it even more suitable to put in a place where there was an existing plant because you don't have to rezone the area for that and unnecessarily aggravate a lot of the public perception of what living next to a nuclear plant is like. We're capable of black start, what they call black start capability. We don't require any offsite power to start up a unit. We have first responder power, so after a total system grid, we could be one of the first responders back. Our systems, if we have a loss of a grid, all the modules, they trip their generators from their source, but all the steam gets 100% diverted and the reactors stay at 100% power, except for one unit that you would need to supply your house loads for your station. Then if there was an immediate return of power necessary, you already have your secondary system and your reactor running. You just have to ramp up the generator and sync it to the grid and start generating electricity. That's what we call the island mode. There's a picture of a palm tree in the simulator, which unit is designated as the island mode unit when it's running because it measures the health of the unit, picks the healthiest unit to be the island mode unit. Beyond base load, mission critical facilities, we're designing to be very friendly with wind and solar as far as ramping rates for electrical generation. By being smaller reactors, we can ramp reactor power fairly quick, and if we need to ramp more electrical load, we can always bypass steam around the turbine and ramp electrical load faster than what the reactor would need to be. And the same thing, if you're raising power, you could have the reactor at 100% power and you could stop bypassing steam, putting more steam through the turbine and ramp up your electrical output faster than the reactor could do a power ascension. Desalination, hydrogen production, oil refineries are all something that would play very well with a NuScale plant. Initially, we did a lot of desalination studies. One unit alone can make 77 million gallons of clean water per day. You can multiply by 6 for power output and water. And there's some examples for a 4-module plant. Hydrogen is everyone's talking about hydrogen now. We're in works with other groups to develop using some steam and some energy from a NuScale plant and electricity to do electrolysis actions to generate hydrogen. That way it's a kind of a storage mechanism for the energy if you have excess. Our design, we can make about 2,000, little over 2,000 kilograms per hour of hydrogen, about 50 tons a day with one single module. Our first exploration into this is the high temperature steam electrolysis. So there's some work to be done there, but it would be something that would work well with a steam and electric plant design. A map showing countries that have established national hydrogen strategies. So a lot of countries are looking into deployment of hydrogen storage and generation. There's a lot of US support for hydrogen with the Department of Energy. And they've sponsored quite a few pilot projects. One, David Bessie in Ohio has a DOE funding to start producing hydrogen on their site. Hydrogen enables decarbonization across all kinds of sectors. So it affects transportation. You can use it for ammonia, fertilizer, metal production, chemical, industrial. I was at an EPRI conference right before COVID shut things down. And one of the things I found very interesting about their projection is you could use hydrogen in the existing natural gas distribution system up to 4 to 5% without having to change out a lot of equipment or components or storage or that. So it could be just, you already have the distribution of it, and it would be a very simple transition to go to in your natural gas. So the high temperature steam extraction offers high capacity factors, does not require significant land mass to achieve the production scale necessary. Again, we can get about 50 tons a day based on our calculations for one module. If you want to just divert one module to producing hydrogen, while the other modules that you had were producing commercial electricity, that would be fine. So the hydrogen, the generation that we're looking at for hydrogen generation connected to a NuScale reactor plays very well because there's some power changes and steam changes that need to happen, so that it fits very well. And we actually backfit some of our steam plant designs to be able to accommodate this when it becomes more viable to bring to market with this technology. Hydrogen also can be used used in fertilizer production. So we could get about 1,150 tons of ammonia production. And petroleum refinery, the same thing. If there's processed steam, they would need electricity for oil refinery. The NuScale could easily provide that. Steel mills. Says we got a 8-module plant would match a typical large-scale ammonia plant. So you could use your cleaner electrical generation to produce these products. Idaho National Labs are doing a lot of research with hydrogen. We're also going to be implementing how a hydrogen plant generation would work inside the control room simulator. So there's going to be some activities to add that into the mix for our simulator control room. Right now, I think about 400 to 500 degrees Celsius is the temperature you need to actually generate this high temperature steam electrolysis. So we would use the steam that we could generate, which is about 500-600 degrees from a NuScale plant, and then you electrically would heat it from there. So I think our big push is like, do you think you can maybe figure out a way to get that down closer to 600-700 degrees Fahrenheit, and that way we wouldn't have to add so much electricity to get it to the right temperature. So that's all on the hydrogen generation side. So we're trying to change the power that changes the world with that design. So I'll be happy to answer any questions about the NuScale design from that aspect, if there are any. Yes. Sure.
So, I'm worried, I like nuclear power. However, I'm worried we're trading one poison back into the ground for one we're trying to reduce CO2 in the air. So, what do you give nuclear step up?
The spent fuel will be put in the spent fuel pit, similar to conventional, and then dry cast out. They're half the size, so we'll be able to stack them. For the same container, we'll be able to get more rods in there. So it's a 50% gain in storage for how you're storing that. We're also working. There's a lot of companies that are exploring recycling the spent fuel. And that we'd be very interested in that. And we've also looked, there are some advanced fuel designs that we're also would be able to retrofit in the future. It was a lot easier initially to get a plan approved from a safety perspective to use the current conventional available fuel that's out there and then transition later.